The common damage mechanisms in CCUS process, understanding typical issues affecting carbon capture systems. Overview of CCUS process, introduction to CCUS and integrity challenges. Carbon capture, utilization, and storage, CCUS, systems are engineered to reduce industrial carbon emissions through the sequential processes of CO2 capture, compression, transport, injection, and long-term geological storage. Each stage introduces unique mechanical, chemical, and environmental stressors that place significant demands on materials and equipment. For engineers focusing on system reliability, understanding these environments is critical. The capture stage involves chemical solvents or membrane systems that can degrade and create corrosive byproducts. Compression and transport stages subject materials to high pressures and potential moisture-induced carbonic acid corrosion. Injection and storage environments present additional challenges, including supercritical CO2 interactions with brine, temperature cycling, and microbiological activity. These varying conditions create a wide spectrum of possible damage mechanisms, from general corrosion and pitting to stress corrosion cracking and scaling. Recognizing the specific risk factors at each stage helps engineers design more robust systems, select compatible materials, and implement effective monitoring strategies. Amine system corrosion, amine stress corrosion cracking, SCC, oxygen-induced corrosion in capture units. Amine-based capture systems, especially those using MEA, routinely face corrosion challenges that arise from the chemical instability of amines under operational stress. Elevated temperatures, oxygen ingress, and reactions with acidic impurities such as SO2 and NOx lead to the formation of heat-stable salts. These salts increase solution acidity, degrading both amine performance and material integrity. Corrosion tends to be most aggressive in rich amine sections where CO2 loading is highest, promoting acid formation and localized attack. Engineers must evaluate solvent composition, filtration efficiencies, oxygen control, and thermal exposure to predict corrosion behavior. Corrosion often manifests as uniform thinning, but in severe cases, pitting and cracking around welds may occur. Material selection, including stainless steels or liners, may mitigate some risks, but solvent management and heat-stable salt reclamation remain essential strategies. Amine SCC is a significant threat to carbon steel and low-alloy steels operating in high-temperature, high-amine concentration environments. This mechanism is influenced by tensile stresses, especially those in weld heat-affected zones where metallurgical transformations increase vulnerability. Heat-stable salts intensify cracking susceptibility by increasing solution aggressiveness. Engineers must consider residual stresses from fabrication, operational temperature control, and solvent condition monitoring. Thorough inspection routines using UT or surface crack detection are critical. SCC typically exhibits transgranular cracking morphology, and once initiated, it propagates rapidly, making early detection essential. Air ingress into amine absorbers introduces oxygen that reacts with amines to form organic acids, peroxides, and degradation compounds. These oxidation products can greatly enhance corrosion rates, particularly in carbon steel systems. The presence of dissolved oxygen increases redox potential, making the environment more corrosive. Engineers must ensure system integrity by minimizing leaks, maintaining proper pressure control, and regularly monitoring solvent oxidation markers. Oxygen-induced corrosion often appears in absorber top sections, lean amine coolers, and storage tanks. Material upgrades or oxygen scavengers may be necessary for high-risk systems. Carbonic acid corrosion from moist CO2, impurity-driven corrosion, SO2, NOx, H2S, O2, erosion corrosion in high-velocity pipelines. During CO2 compression and transport, even small quantities of water can react with CO2 to form carbonic acid, H2CO3. While dry CO2 is non-corrosive, moist CO2 environments lead to uniform corrosion in carbon steels. The corrosion rate depends heavily on temperature, flow velocity, and water solubility. For engineers managing pipeline integrity, dehydration systems are critical to maintain CO2 water content below threshold values. Low spots and dead legs where water can accumulate are especially vulnerable. Corrosion products may temporarily slow corrosion but are unstable under dynamic flow. Pipeline design must consider drainage, pigging, and real-time corrosion monitoring. Impurities in captured CO2 significantly modify its corrosivity. Acidic gases such as SO2 and NOx form strong acids when hydrated, greatly accelerating corrosion rates. H2S introduces the risk of sulfide stress cracking, particularly in high-strength steels. Oxygen, although typically unwanted, increases redox potential and destabilizes protective films. Engineers must evaluate impurity specifications to ensure pipeline materials remain suitable. Impurity interactions can create highly localized corrosion, necessitating stricter dehydration, impurity monitoring, and use of corrosion-resistant alloys in critical zones. High-velocity CO2 streams, especially those containing particulate matter or droplets, can cause erosion corrosion where protective films are mechanically removed. This is commonly observed at elbows, tees, and sudden diameter transitions. Engineers must design piping with smooth flow paths, appropriate radii, and minimal sudden disruptions. Flow modeling can help identify high-risk zones, while internal coatings and periodic pigging mitigate erosion. The synergy between mechanical wear and chemical attack makes erosion corrosion particularly dangerous because it progresses faster than either mechanism alone. Corrosion in supercritical CO2 environments, brine CO2 mixed corrosion and scaling, microbiologically influenced corrosion, MIC. Supercritical CO2 has properties of both liquids and gases, allowing it to diffuse into materials while maintaining high density. When even trace amounts of water or brine coexist, carbonic acid formation occurs, leading to uniform corrosion or pitting in susceptible alloys. Downhole materials face high pressure, temperature variations, and chloride-rich brine exposure. Engineers must select appropriate chromium-containing alloys, assess cement sheath integrity, and evaluate packer fluid compatibility. Corrosion behavior becomes highly dependent on local geothermal conditions, making modeling and laboratory testing essential. When CO2 dissolves into formation brines, a highly corrosive environment develops due to carbonic acid and elevated chloride concentrations. This environment encourages pitting, crevice corrosion, and underdeposit corrosion. Additionally, scaling from minerals such as calcite, anhydrite, or iron carbonate can form on tubular surfaces. These deposits trap corrosive species beneath them while restricting flow and increasing pressure. Engineers must account for reservoir chemistry, scale inhibitor dosing, and flow regime modeling. Over time, these interactions can significantly impact well integrity and injection performance. In CO2 storage and associated water handling areas, microorganisms such as sulfate-reducing bacteria, SRB, can proliferate, forming biofilms that create localized corrosive environments. MIC often results in deep pitting and unpredictable damage rates. Biofilms alter local chemistry, producing acidic metabolites and hydrogen sulfide, which further enhances corrosion. Engineers must implement biocide programs, monitor microbial populations, and design systems that minimize stagnant water zones. MIC risks can increase during intermittent injection or extended shutdowns. Material selection and protective systems, corrosion monitoring strategies, inspection planning using risk-based approaches. Effective mitigation of CCUS-related damage begins with selecting materials compatible with expected CO2 compositions, temperatures, pressures, and impurity levels. Options include carbon steels with corrosion control measures, stainless steels, and corrosion-resistant alloys such as 13CR or duplex steels. Internal coatings, liners, and chemical inhibitors further protect vulnerable components. Engineers must balance material cost, mechanical performance, and long-term corrosion resistance. Material selection should be validated through laboratory testing and predictive modeling based on operational conditions. Maintaining integrity throughout CCUS systems requires proactive monitoring, including ultrasonic thickness measurements, corrosion coupons, electrical resistance probes, and intelligent pigging tools such as magnetic flux leakage or caliper pigs. Data from sensors and inspections allow engineers to identify corrosion trends, detect hotspots, and adjust mitigation systems. Monitoring is especially important in pipelines where moisture ingress or impurity fluctuation can rapidly elevate corrosion rates. Integrating monitoring data into digital twins or integrity databases enhances predictive maintenance. Risk-based inspection (RBA) methodologies help engineers prioritize inspection activities by evaluating likelihood and consequences of failure for each system component. Parameters such as corrosion rate, operating conditions, material susceptibility, and failure impact inform inspection intervals. RBI enables optimal resource allocation while maintaining safety and compliance. For CCUS systems, RBI is particularly valuable due to variable impurity compositions and evolving operational environments, requiring continuous reassessment and adaptation of inspection plans.